So our next topic is to look at what happens to delta G when we aren't under standard conditions. So a lot of times if we're doing this room temperature that people seem to think is 25 degrees, but never seems to be the case for the rooms that we're actually in. But we don't always meet the other criteria for standard conditions. So a lot of times what we're working under are non-standard conditions. So I want to look at this with an example. So something that you know happens, you can observe this while you are at home watching this video. You could also observe this if you wanted to dump some water on the floor, I guess. But we know if you have liquid water, so maybe it's a puddle, maybe it's just a little bit of a spill, maybe it's just, sweat droplets that your body produced, that the liquid water will evaporate, right? So liquid water will turn into a gas. And it will definitely do this at 25 degrees. So if we go get some delta G formation values, calculate a delta G reaction, we get plus 8.5 kilojoules per mole, or maybe just kilojoules, right? If we're going to write it next to this reaction, since it goes with the balanced reaction. That is a non-spontaneous or a not favorable delta G. Okay, but we know this happens without outside intervention. So slash is a favorable reaction under the conditions that we see it, even at 25 degrees. So the issue is that we'll say the in real life version is not standard conditions. Even if it's 25 degrees, remember that's only one part. The other part of standard conditions is that, so the liquid has to be pure. Okay, we could assume that we have pure water, so that would be fine. But the pressure of any gas has to be 1 atmosphere for it to be standard conditions. The pressure of water vapor is definitely not 1 atmosphere. We would all have a very hard time breathing if the pressure of water in the air was 1 atmosphere, right? It's actually a lot lower than that. And funny fact, your favorite appendix has vapor pressure values for water. So what that tells you is that at a specific temperature, what is the pressure of water vapor in the air? So if we go to the appendix, if we're under normal conditions at 25 degrees Celsius, the pressure of H2O is 0.0313 atmospheres. Now, some places list this in torr. If it's listed in torr, you would convert this to atmospheres just by dividing by 760. So much less than 1 atmosphere. We need to get this accounted for in our equation that lets us calculate delta G. And so what our equation will reflect, so our delta G without a circle reaction, it is the standard delta G reaction with some factor that lets us account for where the reaction is at and which direction it wants to move. So what we tack on here is RT times the natural log of Q. This is the same Q as before. This is the reaction quotient. So I hope you haven't forgotten about Q. If you did, there's a video for you to go back in the equilibrium section to look at about the reaction quotient, how to calculate it, and what it means. So for our reaction, if we're going to do Q, we need essentially an equilibrium constant expression because Q takes the same form. Well, pure liquids don't appear in the equilibrium constant expression. So for our reaction, Q is just equal to the pressure of the H2O gas. So honestly, we don't have to calculate Q. We just have to plug everything in. Okay, so delta G reaction equals our standard value, which is 8.5 kilojoules per mole, plus RT ln of K. Well, the R value, the 8.3141 is in joules per mole Kelvin, so we need 8.314 times 10 to the minus third, so it'll be in kilojoules per mole Kelvin, times 298 Kelvin, times the natural log of 0.0313. So this, in the end, gives you negative 0.0856 kilojoules per mole. So not by very much, but we did get a negative value. Therefore, under the non-standard conditions that this is actually operating, this is a favorable or spontaneous process. Okay, now if we're talking about Q, we may as well go ahead and relate all of this to equilibrium because it's all connected. So when a reaction is at equilibrium, one thing that we know for sure is that Q is equal to K, and something you might have kind of figured this out, but maybe not. Delta G, without the little circle, so non-standard delta G, is 0, right? Our reaction isn't actually going forward or backward. It's neither spontaneous nor non-spontaneous. So it's neither favored nor non-favored. So my delta G is exactly equal to 0. If I were to plug those values in and do a little rearranging, I can calculate a standard delta G reaction by doing minus RT ln of KEQ. So now, if I know delta G reaction, I can get the equilibrium constant. If I know the equilibrium constant, I can get delta G reaction. Now, this should track with your understanding of equilibrium, right? If K is less than 1, this is a reaction that favors reactants. So it doesn't want to go very far to the right. That's a non-spontaneous reaction. So delta G is positive. K greater than 1 favors products. So the reaction wants to go to the right. This is a negative delta G or a spontaneous or favored reaction. With all of this, it means that you can now have problems that you need to do. We're back to it doesn't look like I have enough information to do this problem, but I guarantee that you do. So, the practice problem that we're going to look at is that you are asked to calculate KEQ for the reaction N2O4 gas in equilibrium with 2 NO2 gas at 298 K. And And that's it. This is all that you're given. It feels like you don't have enough information, but we have now an equation that relates KEQ to delta G, and we have data tables. As long as we're at 298, we have data tables that will let us get the delta G. So our plan for this is we'll use delta G formation values to get delta G reaction, and then we'll use delta G reaction to calculate the equilibrium constant. So if you want to give this a try, this is a really good place to pause the video and try solving this problem before watching the rest of the solution. In fact, I will put the rest of the solution a little bit further down the page so that you have a place to pause and a little bit of a break. Okay, so the delta G standard reaction using products minus reactants. So the products are two NO2s. So if I go look up delta G formation for NO2, it's 51.3 kilojoules per mole, minus 1 times 99.8. So my delta G reaction is 2.8 kilojoules, and it's positive. So this should prepare me to get a small equilibrium constant, right? It's a non-spontaneous or not favored reaction. I should have a small KEQ. Well, the reaction or the equation that's set up for this is not the most convenient, right? Minus RT ln of KEQ. The thing that we need to solve for is inside a natural log, so let's just rearrange this a little bit. The KEQ is equal to E, because remember that's how we get things out of natural logs, to the negative delta G over RT. So for my reaction, that's negative 2.8. This time I'm going to convert this to joules, so times 10 to the third joules over 8.314 joules per mole Kelvin times 298 Kelvin. E to the negative 1.13 is 0.32. So a small equilibrium constant, which is exactly what I was expecting.